Sergei, the room is yours.
Thank you. Hello, everyone. My name is Sergei Shevchenko. I work for Sophos. I'm a threat research manager. And our team specializes in analysis of Linux, macOS, and Android threats. And today I would like to talk about an interesting sample that affects macOS platform. You will see the techniques employed by this sample. It belongs to PUA, so-called potential unwanted application, so it's not malware. Before I proceed and describe the internals and some techniques employed by this family, I have to make a little disclaimer that I can't name the company behind it because it's a company with lawyers and they're not happy when we present something like that. So the name of this particular family will not be named, but you will see the techniques and we definitely detect it. So let's proceed. And before we get to the technical details, just a little bit of overview of what we're dealing with on macOS platform. So generally speaking, malware is not, if you look at the sheer volume of the samples, that malware represents around 6% of all the infections, with the bulk of the samples coming from PUAs. If you look at the, because we get the telemetry, we understand the threat exposure rate, so that is how many customers have been attempted to be infected where a product has blocked the infection. And if you look at the number of PUAs, then you'll see that around 16% of the customers were prevented from being infected, while 1% corresponds to malware prevention. I won't touch the top malware families. It's not that interesting. There are not too many of them. But if you look at the top PUA families, then it's a crowded space. There is a bit of competition. The bulk of the reports come from MacKeeper, followed by Genio, Advanced MacCleaner, Install Core, bundleware, and other families. So let's proceed and a little bit of background. How does this family distributed, how does the system work? And you have to realize that there are many legitimate developers out there that build good software, right? And the software that build, it's often contaminated with GPL, so they have to release the source code, and once it's released, they can't sell it, because if they start selling it, anyone can pull the source code from GitHub and compile it and use it for free. Nevertheless, the software is useful, and I myself use some of that software, and I'm pretty sure you use it as well. I won't name it again, because you have to understand that the developers of that software, they're looking for the ways to seek for reward, to be rewarded for what they build. So to get some kind of compensation, monetary compensation, they approach this company, and this company bundles their software, produces the installer, gives it back to them, they put the installer on the website, customers go, fetch it, run it, and this is what they get. That's this just normal installation process. The DMG file gets mounted, and they run the installer. The only difference is, at the end of the installation, the customers will end up with having the original software installed. At the same time, they'll end up with some side effects on the system that they were not willing to have or not happy with. The forums are flooded with the posts when people complain about some dodgy browser extensions or plugins being installed that replace search results, and they're asking for help to understand how to get rid of them. So, okay, let's have a look. That's the mechanics about how, that's how it works. That's how money works in this scheme of things. By the way, the company behind this installer claims they have millions of installations. I don't know if that's true or not, but this is what they claim on their website. Okay, let's proceed and have a look at the some technical details of this software. So it all starts with the DMG file gets mounted. We have a look at the structure of the DMG file, and you'll notice there's a main executable file. How do you know it's main executable? You look at the P list, and in P list you have a key called CF bundle executable, which specifies the name of the main binary, main executable, and that's the name. This family is interesting because it's using English words, but the words themselves are weird. They sound like English words, but I never heard of the words like senectitude or sphenobasilic or cocon secreto. So that's the good sign. If you see that kind of main executable, it's a good sign you're dealing with this particular family. The main executable itself is signed. So when you run code sign utility, you see there's always a valid digital signature. We see maybe a dozen unique samples a day popping up on Aristotle. And each time it's a random file name, and each time it's signed. So if it's signed, it means it bypasses a gatekeeper, gets installed on the custom system with no questions asked from the operating system, from macOS. How do we analyze it? We have a look. First we look at the entropy of the file. So the flat entropy of this file, that you can see, bulk of the file has relatively flat entropy. What does it tell you? It tells you that most of the file, probably 95%, is either packed or obfuscated. It's not a valid code. The entropy that's jumping up and down at the start of the file, that's the actual code. And where it's also noisy at the end of the file, that's where the digital signature is, because it's in clear text. So that already gives you an idea that the file itself most of it is packed. Okay, what do we do next? We load it into IDA, right? Golden standard disassemblers, and you load it up. It shows up as a Mach-O binary, and that binary lies on Objective-C runtime, libopc dilib. And if you look at this disassembled code, you immediately see that at the entry point of that executable, there are some bytes which do not translate to valid code. So there is no code to execute at the entry point. So how does it run? How does it execute if it doesn't have the code? Is it actually a valid executable? Would it crash? Would it run? And the answer is in the concept of lazy and non-lazy classes. That's a concept that exists on macOS platform, and Apple calls it lazy classes are the classes that are not realized immediately. They are realized on demand, the moment they get the message or the method from that class. As opposed to that, there are non-lazy classes, the eager classes. Those are the classes that get realized immediately when the program starts. And what's also interesting is that these classes, the non-lazy classes, will always implement a method called +load. That's the method that gets called. Now, let's have a look at the actual source code of the Objective-C runtime. When I did the slides, I saw the source code published by Apple, but then I pulled it and it was not available. I don't know why, but I could still find it in Web Archive. But nonetheless, that's the Objective-C runtime new.mm. That's actual source code of the Objective-C runtime. And if you look at the source code to understand what it does when it loads the Mach-O binary, you will see that it calls this function called getObjC2 non-lazy class list. That function will return the list of classes, non-lazy classes, into this list, class list, and then for each member, for each list in that, for each class in that list, it will call a function called realize class. If you look at the actual function, where that function is specified in the macro getSect, and right here you can see __objc NL CLS list. That stands for non-lazy class list. That's the name of the section inside the binary from where the loader obtains information, descriptors of the non-lazy classes, and then it calls the +load method of those non-lazy classes before it calls the entry point. So what we do, we go back to IDA and we say jump to segment, and we specify the name of the segment. It will be enlisted right here, OPC NL CLS list, and IDA will jump into that declaration, and right in that place you will see two classes. Again, random names like listed upaythric. That's the non-lazy class which will have +load method. So the loader will call that method first, before it calls the entry point. If you proceed to that +load method implementation, you will see that in that method, there is an actual code, actual valid code that can run, that can execute. And right here you can see this interesting construction that basically assembles a string. And the string is VM_protect terminating 0. So it compiles that string character by character in the random order. And if you run, even if you use a freeware version of IDA with a built-in debugger, you can debug it, you can trace that code and to understand what it's doing, because visually, you can recognize visually what it's doing, but if you trace it, it's just easier. And I'm gonna trace it now. So you see it puts C_O0R_M, followed by T, followed by V. So character by character, it constructs that string. Once it is constructed, it will call DLSym. DLSym is the equivalent of the Windows get proc address to retrieve the pointer into the function implemented in the library, and then it will call that function by the pointer. So it doesn't want to expose the name of the actual function it's going to call. It's hiding that by using this little trick, which is pretty common for Windows malware, right? But not. It's really rare to encounter something like that on a Windows on a Mac platform. In some way, it reminds some like a ransom note because they want to conceal it. Okay, so how does it run VM_protect? First, VM_protect function is used to assign certain protection flags to a chunk of memory. And it takes 5 parameters. And you can see right here, so it uses its own task, and then what it does. So imagine this is the code section, right? In that code section, there is some variable it's called here encode, but you call it anything you want. You can call it marker. The encode itself has an offset within that code section. So it's doing what it's doing. It takes the address of that encode inside the code section. Then it subtracts the offset of that encode inside the section. That way it gets to the start of the section. And following that, it takes all 14,322 bytes, which is the size of the code section. And then it assigns VM_prot_all flag, which is a combination of read, write, and execute. So initially, the section has the flags read and execute. That's all the loader needs, read and execute it. But it wants to modify it, so it assigns one additional flag, write flag, by setting up VM_prot_all. The analogy is, imagine a street with 12 houses, so it takes the house number 3, subtracts 2, and takes the whole length of the street, which is 12 houses. It could have just taken the whole section from start, but this is how it's doing it. After that, it decrypts the code section by using 32-byte XOR key. Again, in each executable, that key is randomized. It's always different. If you look at the encode itself, it's represented some gibberish bytes which have no meaning at all. Okay, so what we're going to do next is let's use the debugger built into IDA. And in this tracing, what's happening, it takes the code section, it allocates a memory area, chunk of memory, equal in size to the code section. It then decrypts the code section into that memory area, and then it writes it back into the code section. And after that, it calls the entry point in that code section. So right here, I'm going to trace that decryption loop. But at the same time, I'm showing you the memory area that corresponds to the encode. Right now, it's zeros, right? So there's the newly allocated memory. But if you actually run it, if you trace that code, it will execute. But while it's executing, keep an eye on this memory area. What happens to it? This is what the encode itself gets decrypted into. So it gets decrypted into a name, Maxim Maximovich Isaev. Does anyone know what that means? Yeah, I was born and grew up in the Soviet Union, so I know that name very well. But before we get to that, let's have a look again what's happening. So this is the decrypted code section. Now, it has valid code in it. You remember there were gibberish bytes in it before it was decrypted? Now it has a valid code, so now it can run. This is the encode inside the encrypted section before it was decrypted, and that is the encode after it was fully decrypted. So back to the name, Maxim Maximovich Isaev is a real name of Max Otto von Stierlitz. Think of him as a Soviet or Russian James Bond, extremely popular. From the book, persona from the book and the movies, I grew up with this movie, right? So immediately hit home. Why did they put that name into the code? I don't know. It could be just a Mach-O or a hidden Easter egg. I don't know. But once you uncover it, it kind of makes your day. It becomes interesting and intriguing. What happens next? I think I owe you to explain the title of this presentation. What does it mean? Never before had Stierlitz been so close to failure. That's a common phrase in Russian, used to describe a situation when someone's cover is about to be blown, and someone's, not necessarily spy's, cover. So what happens? Let's have a look again at the whole picture and recap the process from the start. So from the very start, this is the encrypted code section called __text. It has an entry point in it. It's encrypted. The code itself is encrypted. But the execution, the workflow itself, starts from the dynamic linker locating the non-lazy classes declared inside the executable, finding them, finding the +load method, calling that method. After it's called, the actual method will take that encrypted code section, it will decrypt it, and then, only then, it will pass control into the entry point in that code section. What that code will do next, it will take the compressed blob, it's a large chunk of data, it will lift it from the file. So you remember the entropy, that's actually compressed blob. So it will lift it, it's about 300 kilobyte in size, it will decrypt it, it will decompress it in memory. So it will be something like 900 kilobyte module or a chunk of data. For starters, chunk of data. But then it's using an interesting trick to inject that with undocumented APIs, to inject that memory chunk into the address space of the process. So it's a injection of that module will be similar to how Windows loads, dynamically loads DLL. So it's doing the same thing, only using undocumented trickery. Once loaded, that method represents itself a very powerful engine driven with the tasks. And the tasks themselves that specify what exactly the engine has to do are fetched. Some of them are locally stored, but some of them are fetched from the remote server. So whatever the admins of the software decide to put on the server, that thing will fetch those tasks, and those tasks will be executed by the engine. Okay, so now we analyze the engine, its capabilities. And the one thing is it's capable to detect the presence of the virtual machine. So again, does it ring any bells? So what the malware on Windows is doing, right? So internally, they call that function check possible fraud. And the one possible explanation is that if we imagine this installer being submitted by some people to different sandboxes, and each time it runs, does it mean that the company has to pay the money, each time pay the money to the developer? Does it mean that it's possible to game the system? They don't want that situation to happen, so they consider it to be a fraud, and they detect the presence of the virtual machine. The detection itself is based on a number of tricks. First of it is they check the MAC address. The common VM manufacturers, they have hard-coded MAC addresses. Like for instance, 001C42 stands for Parallels VM. That's a common MAC address for the Parallels VM. Internally, they're able to recognize 35 virtual machines, over 35. And that's just the list. By the way, what I didn't mention here is that all these strings and APIs in that engine are encrypted, and there are more than 1,000 encrypted strings which are decrypted by more than 1,000 unique functions, and all of them are randomized. So if you take another sample, it's totally different strings, totally different functions. It's all randomized. So we had to build the scripting to automatically decrypt all the strings and patch the binary, disassemble it again to understand what exactly the engine is doing. The other trickery to detect the presence of the virtual machine is things like get host UID, DADs create from BSD name. They query the USB vendor name, so the drivers often have the telltale signs in their names that specify the virtual machine manufacturer. Display ratio, they look at it. Mouse position, since the last mouse movement, they look at the mouse is moving. So if it's an installer and it's getting the clicks and proceed, people normally work on Macs by moving the mouse and clicking. So if there is no mouse, or if the mouse is not moving, it's a telltale sign it's a virtual machine. System uptime since the last reboot. So if you run this family or this sample in a virtual machine in a sandbox, after running it, the sandbox has to restore the clean snapshot from the image. Once restored, the system uptime will also be reset to the previous value. So it's a fingerprint. It's a VM fingerprint. By checking that, they are aware that it's actually not a real system. It's a sandbox. Full path file name of the engine files, because the sandbox can call it something, that they can give it some generic name. And okay, so that's fingerprint. I mean, it's understood. Now, if you look at the total scope of the engine capabilities, it's a fully functional backdoor. It has a dedicated browser manager that can set new home pages, terminate browser process, screenshot controller that takes full screenshot, takes the screenshot where the mouse is clicking the screen. System controller, it collects all sorts of system information. If you plug in your iPhone to your Mac, it will read device class, ID, serial number, whether it's iPod, iPad, iPhone. Add remove applications, check the presence of VM, as I mentioned, collect the list of all the installed and running applications, collecting cookies from the browsers. It can search recursively for files. So I can't say attackers, the admins can specify the task to search for files recursively. It will find those files. It can upload those files. It can download files. It can run those files. It's a full file system access. It can display alerts, run applications as root, copy more files, save data, create, delete directory. It's a fully functional backdoor. Now the question is, when you look at it, you probably have a question, why so much power? And the answer is, I have no doubt that the actual intention was to provide full visibility over the software, because the company is so careful to protect it, where it's deployed, where it's running. They are so keen to prevent the fraud situation when people are trying to game the system, that they want the telemetry, they want full control, and they have set it up. They set up a full backdoor. So what conclusions can we draw from this? First, it's a very popular bundleware product. They claim millions of installations. We see sometimes dozens of unique samples a day submitted to Aristotle. They regularly change the encryption scheme. By the way, the Stierlitz that I mentioned previously, this talk was published on 4th of April. In 2 days, they've changed the encryption scheme. So Stierlitz was gone, and they added another obfuscation layer. Another time it was changed was just a week ago. Just a week ago, they totally reset the encryption scheme. Each time it happens, if you look at the Aristotle, the detection rate drops immediately. Then it gains slowly, one by one, day after day, it gains and increases. But each time they're very careful to drop that detection by regularly changing the encryption schemes that they employ. Backdoor unlocks full access to the system. Memory injection is simply copy-pasted from the Mac hacker's handbook. The engine itself is driven with a symmetrically encrypted remote task. So again, the question is, what happens if someone overtakes control over the command and control server? What if someone intercepts the traffic and injects malicious tasks? They will simply they might potentially overtake control over that system. And on a final note, this is just a trend we are witnessing, and that trend is the spilling of the techniques which are so common for Windows world. Every Windows analyst, researcher has seen it millions of times. There is no point of repeating it, but if you look at it, it's code obfuscation, it's API, string obfuscation, it's dynamic loading of the modules in memory. Anti-VM, they have anti-debugging techniques. They call ptrace with deny attach function, so that if you debug that executable, it will crash. If you run it and then try to attach the debugger, it will throw an exception and still crash. It's all there in this code, and that's what's happening in the world of Mac. It's just kind of important to understand that. And this is it. That's the end of the presentation. Thank you very much. If you have any questions, please.